Okay, so we're back in section 5.2, and we're our goal is to understand the definite integral. So the definite integral is basically a nice way to indicate the area underneath a curve. So suppose we have start with a continuous function. And we go from on the x-axis A to B. Then we learned previously that we can calculate the area underneath a curve, at least a curve that's above the x-axis, with a Riemann sum, right? So the area above the x-axis is considered positive area. Okay, so think of this as A1 and A3. Now, instead of using rectangles that are above the x-axis when the function itself is below the x-axis, we can use rectangles that go into the negative territory. So what we would say is those areas would be of the form delta x times f of xi plus delta x times f of xi plus 1, and so forth. But these terms here are negative, right? So we're considering the area of a rectangle below the x-axis as a negative area, just because delta x is positive, is the width of each rectangle, and the height of the rectangle is negative. So this area here, we can call this one negative A2. So what we define is the integral from A to B of f of x dx. It would be the area 1 minus that area 2 plus this area 3. So the integral is a signed area. And in fact, as we'll see later on in our lesson, the integral, let's say this is from 0 to 2 pi. Let's say this is the sine of x dx. According to our definition, we would expect that this would be 0. So this positive area would directly cancel out with that negative area. Okay, so let's take a look at the definition again. So the integral from a to b of f of x dx is the limit as n goes to infinity of the right approximation Riemann sum for your function. So it's a sum of height times base, height times base, height times base. But just keep in mind that some of these heights could be negative, like so. And if this limit exists, we say that f is integrable on the interval from a to b. So we're going to be exclusively looking at functions that are integrable. Okay, delta x, once again, is b minus a divided by n. And x1, your first endpoint, would be a plus delta x. So you start at a is your leftmost endpoint, and then you shift to the right by 1 delta x. x2, you shift to the right by 2 delta x's. And xn, You start at A and you shift to the right, n delta x's. All right, so let's try a little example here. We have the definite integral from 0 to 3 of x cubed minus 6x dx. So let's try to find the R6 approximation. Okay. So we're going from 0 to 3. And we want to split the the region into 6 boxes. In this picture, I wrote it with 8 boxes just because it's easier to make 8 boxes than 6. So let's try to come up with 6 boxes that are equally spaced. So and we're using the right endpoint as the approximation. All right, now notice how some of the boxes are below the x-axis, some are above. And we're starting at 0, and we're going to 3. So let's calculate delta x. So it's b minus a over n. 3 minus 0 divided by 6, which is simply 0.5 or 1/2. So that's equal to 0.5. Okay, and well, let's write down the R6 approximation. So it would be 0.5. Take out the delta x. Right, we factor out the delta x. And the first subdivision point would be right here at 0 plus 0.5. So we shift over by 0.5, then 1, 1.5, and so forth. Okay, we need to plug in the function. So let's call that f of x. So f of 0.5 plus f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3, where f of x is x to the 6 minus 6x. All right, so take a minute to try to evaluate that Riemann sum. If you do it correctly, what you should get is 1/2. So when you plug in f of 0.5, 0.5 into, this is an x to the 3rd power, sorry. When you plug in 0.5 into x cubed minus 6x, you're going to get negative 2.875. When you plug in 1, you of course get 1 minus 6 is minus 5. When you plug in 1.5, you will get negative 5.625. When you plug in 2, you should get minus 4. When you plug in 2.5, you should get a positive number, 0.625. And when you plug in 3, you should get 9. All right, so here's a better picture of our boxes. Notice we took the right corner approximation. And I highly recommend you try to graph this picture yourself without looking at the answer to make sure you really understand what's going on. All right, so the integral is so this integral is approximation is equal to negative 3.9375. So of course this is not the exact answer for this definite integral, but it is but it is an approximation. Now the calculator can actually do these integrals very accurately using various methods, some of which you'll learn in Calculus 2. So let me show you how you can use your calculator to do this integral. All right, so I have my trusty TI-36X Pro. So second function above the exponentials is the integral button there. And we go from 0 as the lower limit of integration, 3 as the upper limit of integration, and x raised to the third power minus 6x it's calculating, and the actual answer is negative 6.75. So as you can see, our approximation is not very accurate. So the true answer, 0 to 3 of x cubed minus 6x, is negative 6.75. Now we will learn how to do this exactly pretty soon. Okay. Now, we actually can do some integrals exactly using pictures and geometry. So how would we find the integral from 0 to 1 of the square root of 1 minus x squared? So pause the video for a second, but before that, see if you can come up with a way to represent this as a familiar geometric object, and then interpret the integral as the area underneath the curve. So do you recognize what exactly that function is? It's something you know from geometry, and you know from geometry how to compute the area of that object. All right, so if you remember a little bit of your analytic geometry, x squared plus y squared equals r squared would be the equation of a circle centered at the origin. So in our case, solving for y, taking the positive square root, you get the square root of r squared minus x squared. Well, 1 equals r would fit exactly. So for our example, we have circle, radius 1. All right, so let's draw the picture. Now we're only taking the top part of the circle, right? The upper semicircle. And we want to go from 0 to 1. So we're interested in that area right here. So because it is a true circle, we know that the area would be 1/4 of the area of a circle. Radius is 1, so it's 1/4 pi. And of course, we could check this on our calculator, make sure we didn't make too bad of a mistake. So 0 to 1, square root 1 minus x squared. Right, it's thinking. What it's doing is it's basically finding the area of well, there are different methods, but it might be finding the area of millions and millions of little rectangles or something similar to that. All right, if we don't recognize there's a pi in there, just divide out by pi. And as you can see, pretty close up to, you know, eight or so decimal places. So pi over 4 would be the exact answer. All right, that's the answer for part A, pi over 4. Okay, B. We can graph this. So try to graph this and recognize the area also from geometry. So pause the video for a moment and see if you could do that. Okay, so this is the graph of y equals x minus 1. And we want to find the area from 0 to 3. So recognize that these are just two triangles. One is a negative area triangle. One is a positive area triangle. The x-intercept, of course, is 1. And this is xy equals x minus 1. So this is the coordinates of this point is 3, 2. And the coordinates here would be 0, minus 1. So the integral from 0 to 3 of x minus 1 dx is simply that negative area plus this positive area. But we know the area of that little triangle would be negative 1/2 the base times the height, negative because it's below the x-axis, plus the base over this triangle would be 2, so 1/2 the base times the height, which is 2. So one of these 2's cancel, and we get 2 minus 1/2, 3/2. And once again, you could check your work in the calculator. Always a good idea to check your work if you can, especially on an exam. So 0 to 3 of x minus 1. And it comes out very quickly, 1.5. Okay. If you have any questions, be sure to email me, and we can go over them at some other point. Use M5 to approximate the integral from 1 to 2 of 1 over x dx. All right, so this is another Riemann sum calculation where we have to find the area underneath these 5 boxes. So in this case, the function is positive above the x-axis. So we're going from 1 to 2. And you want to split this up into 5 boxes. So delta x would be b, so 2 minus a minus 1 over 5, which is 0.2. So we can fill in these missing subdivision points, 1.2, 1.4, 1.6, 1.8, and 2. Now, to do the midpoint approximation, what we would like is the midpoint of each of these subdivisions, these subintervals. So the midpoint of 1 and 1.2 is 1.1. 1.3, we just shift over by 0.2. 1.5, 1.7, 1.9. So once again, we're just finding an approximation. We're not finding the exact answer. This is an approximation. All right, so the picture would be, so draw a dotted line, and then draw the rectangle with base delta x, 0.2. All right, so the M5 would be delta x, so 0.2, times the height of each box, but the height is determined by the midpoint. So it's 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7, 1 over 1.9. Okay. All right, so that's easy enough to calculate. You could do that on your calculator. The answer, by the way, I think I have the answer here, is the answer is 0.691908. That's of course not the exact answer. As I said, that's an approximation. So it's at the bottom of page 390. Okay. Going back a little bit, so recall that example that we did where we only got negative 3.9375 as the approximation. They do increase the number of rectangles. And if you increase the number of rectangles, the picture looks like this. And as you can see, we are getting closer and closer to that answer that we found using the calculator. This is quite complicated, but they actually find the answer exactly using the limit of Riemann sums. I don't know if I recommend you look at this now unless you're really advanced or you're finding it very easy, but you can do this by hand, this integral totally by hand. And if you do it carefully, you can show that these Riemann sums do approach the answer we got on our calculator. But as I said, we will have a much easier way of doing this very soon using the fundamental theorem of calculus. All right. So the definite integral has some very nice properties. And these properties will allow you to simplify and work with definite integrals. So the first property is a little strange. It says the integral from a to b of f of x dx is negative the integral from, oh, I forgot to change it. So this should be from b to a. So make sure you change that in your notes. So the integral from a to b is negative the integral from b to a of f of x dx. So what's happening there is we just reverse the integral limits. You might wonder, why does that introduce a negative sign, right? So what we're saying is something like the integral from 0 to 1 of x squared dx is negative the integral from 1 to 0 of x squared dx. The reason is when you compute delta x is b minus a over n. So in one sense, when you do it on the left side, it would be, so delta x1 would be 1 minus 0 over n. But on the other hand, for delta x2 over here, you would get 0 minus 1 over n. And as you can see, they're opposites of each other. It's 1 over n and negative 1 over n. So the negative sign is actually introduced via the delta x. So that's why if you switch the limits of integration, you do get a negative sign there. The integral from a to a must be 0. The proof is if you switch a and a, you introduce a negative sign. So the only number that's its negative is 0. But you could also interpret this as the area underneath a single point is 0. There is no area underneath a single point. So it makes sense that we should get an answer of 0. The integral of a constant function dx, well, all that is the area underneath of a rectangle. That's in this way. So the height is c, and we're going from a to b. So, of course, the area is just going to be the base times the height, right? So that's all that integral represents. It's the area underneath a horizontal line. All right, so the definite integral is linear. Linear is a very important concept in math, and what it means is it plays nicely with plus and minus signs and constant multiples. So if you have to take the definite integral of the sum of two functions, you can just work on them separately and then add their answers. This follows because the area of the boxes, the heights of the boxes, are easily computed when you have a sum of two functions or when you have the functions separately. So if you add two functions, the heights of those boxes will be the sum of their heights. So it follows easily from the Riemann sums that the linearity properties. Same thing for multiplying by c. So you can take this constant c straight out, and this c, it just rescales the height of every box in your Riemann sum. All right, this is an interesting one that's used a lot. So let me draw the picture for this one. So the picture that we have here is we're going from A to B to C. So you have some function. It could be negative, that's fine, but I just drew it positive. So A to C and B. So basically what we're saying is the area from A to C is the same thing as the area from A, actually, sorry, I drew it wrong. Let me fix it. So C is in the middle and B is on the right. So the area from A to C plus the area from C to B is the area from A to B. So the big area from A to B is the sum of its parts from A to C and C to B. All right, so we'll continue next time with some of these other more nuanced properties of the integral. So this was your first lecture on the definite integral. All right, so take care, everybody.